Шаг.
Yeah, thank you. Yeah, I continue now. In previous week, we defined this class, small class of maps, and here C from C or n-dimension sphere or n-dimension ball, because this is our generated configurations, and so we can define both localization in this set of maps, because our category proper combinatorial model category, our need only left proper for both localization, but since limits here calculate exactly as exactly object-wise, so it's just inherits and left and right properties with our category of space. Model category of space inherits. Thank you. And also, I should note what in previous times when I formulate proposition about in previous times I said what what if we have a combinatorial model category, coefficient generated combinatorial model category. So for testing what some maps is V equivalence, we enough tested on only on only on C from domain and codomain of E generated configurations, but generated model category. But here also important what model category is left proper. I forgot to say it. Left proper. And
maybe you could remind everyone.
Yes.
What exactly is the underlying category of spaces? We don't consider all spaces. We only want to consider delta generated spaces. So
in real,
what are these?
We need our choice in previous times was delta generated topological space, since we have next important properties. With Cartesian closure be complete and contain CV complex. These three property covered standard convenient category of space, but only Cartesian closed be complete and contain CV complex. But and more classical choice for these three properties compact generated topological spaces. But compactly differential topological spaces, since they construct from a large class objects, all compact Hausdorff objects, with not local presentable category, and with bad if you want to use this powerful machinery, categorical theory, and abstract homotopy theory. So we just do, in my opinion, more natural choice. We just restrict us only space which construct from simplex. So space which topology controlled by simplex and with is the same. Just another way said define this category is just complete clause of simplex in topological space. You just take simplex and add all co-limits of simplex and include all CV complex in particular and more. And with correflective subcategory topological space, if your correflector is delta generalization, so and you can transfer model structure along with correflection adjoint. So I mean, your model structure.
I have a side remark. Not so long ago, it was an open question whether or not there is a convenient category of smooth manifolds. There is a convenient category of topological spaces, which means compactly generated weakly Hausdorff. But what about manifolds? Not so long ago, people didn't know the answer. Has there been any progress?
You mean smooth manifolds or?
There are several versions. To simplify, let's say smooth. Smooth manifolds
when we construct some category which close with smooth manifolds and also give us homotopy theory.
We want basically the same properties we have for compactly generated weakly Hausdorff spaces. Cartesian close.
Be complete, contains CV complex, but not locally presentable because compact Hausdorff objects is large class, and we don't have any small generators. Sorry.
Вопрос был в том, можно ли придумать какую-то категорию, которая содержит гладкие многообразие, гладкие отображения, и, допустим, содержит внутренние формы. Естественно, гладких многообразий просто в буквальном смысле недостаточно, но, может быть, можно к ним прибавить что-то, так, чтобы, у нас получилась, удобная категория гладких многообразий. Еще, некоторое время назад, я бы сказал, там лет 10 назад, люди этого не знали. Но, может быть, люди, которым нужно, не знали, а люди, которые знали, не знали, что такая проблема есть. Что наука до сих пор, куда она продвинулась?
Yes, it depends from some detail what you mean. If you want have subcategory of topological space, so for example, several details we need clarify because if you have two smooth manifolds as objects in this category, which we want to construct, we want what maps between these objects will be the same smooth maps, or it can be more. If we enough just smooth manifolds with potential more maps between these, so delta generated topological spaces.
No cheap tricks. We want a full embedding of.
Okay. So if we want full embedding, we have a very simple and canonical answer on this question. Just take category Cartesian spaces with smooth maps, card in smooth sense. When consider category pre-shifts on this category. This means functors from dual category to sets. You can but you already have full embedding from manifolds here because you can think about manifold how
As
points in manifold, lines in paths in manifolds, and so on. Just representable pre-shifts on this category, in sense manifolds, of course, not in sense card. In card, it is not representable, and but this not I mean, in this category, never mind. It's I just want to say what more natural by many reasons. Take some reflective subcategory shifts and the shifts shifts in sense if we have some open cover, I mean with some Rn object in card. And we have open cover also every V is open subset. I mean yeah, open smooth embedding. Like okay, and it's finite for more good properties. What is it? Finite finite open cover. I mean every open smooth embedding and this selection from coproduct. So for every such finite open cover, we defined what our pre-shifts on U is the same compatible families. So like in a usual topology, Chef condition function on all spaces, particle function on every element covers such that way compatibility on intersections. And this is just a reflective subcategory with very good properties. Is topos, and because we take only finite covers, is every topos every gradientic topos is locally representable category, but your regular kernel can be any big I mean any kernel, but because we take only finite covers with finitary, like simply show set, like any pre-shifts category, finitary locally presentable category, and in real Queen model structure on this category already was I mean it's more or less obvious what you can construct Queen model structure on this category. Just what you have topological space and consider so maybe not so obvious because topological space give us 1 second. No, obvious, of course, obvious. Yeah, we have near functor which send topological space in pre-shifts on this category, because smooth maps in particular is continuous maps. No, like singular simplicial complex is also such functors when we take simplex and only affine map, linear map between this simplex, our singular simplex complex of topological space is also near functor respect this subcategory. So we have near functor and in abstract reasons, always when we have some near functor, you have a left adjoint geometrical realization functor, which just take in usual sense geometrical realization to colimit left Kahn extension, and with a junction, and you just want transfer model structure, clean model structure, and along with a junction. And in real on lab, this category very already was very. I mean, many people study this category many years because it is very close with famous diffeological space. It's just concrete. No, it's also covered smooth sets, and this can many people try do differential geometry in the setting. You can you can say about all conceptual differential geometry in the setting, and this contains diffeological spaces. It's just concrete shelves which which when your path every path in your space defined its points. No, I mean, but how in simplicial sets you okay, I mean, I think it's very...
Я извиняюсь, я значит, свел с рейсом ваш доклад.
No problem, but it's very interesting, but
давайте,
yeah,
нет, я согласен, что это интересно. Давайте мы вот это обсудим во время перерыва.
Okay. Yeah, it's already very far, but
I derailed the talk. So let's go back to our muttons, and then we'll continue this discussion during the break.
Yeah, but in general, I already give answer. But this category very good, contained also smooth manifolds, and because some things obviously give you sheaves and have model structure, and I also can give critical works on archive which study homotopy theory in this setting, and yeah. So we come back to and for now we enough only delta generated topological space, just locally presentable but not finitary locally presentable. But very soon we need finitary locally presentable category. No, I will say about this. And so we have what we have is a junction on pointed topological pointed space, and which we use it, and we can lift it on the category of sequential spectra, just by okay. Now if we have some sequential spectra, we just can take object-wise suspension functor, and and we want maps to, sorry, what I do. we want this map, and of course we can we just can take when sigma n was structure maps in original sequential spectra, and if we want define omega from sequential spectra, we can now we have right when left, this means co-unit adjunction to AN, when unit adjunction, and finally here should be sorry, what's happened? Maps from AN here. Yeah, no unit adjunction, just adjunction to structure map. Yeah. We have structure map, and we take by adjoint we have this. Yeah, this define for these functors. Obviously, sigma no, because in value-wise model structures, these functors obviously preserves, for example, omega obviously preserves fibrations and trivial fibrations. So this is Quillen adjunction for a value-wise model structure. But I will denote what I denote value-wise model structure on category of sequential spectra just like this by default, and stable model structures like this. When I write this somewhere, I mean sequential spectra with a stable model structure. So this functor is left also. Moreover, this functor is left-carrying functor respect stable model structures, and by universal property, left-bound focalization, we just need to show what this preserves via equivalence. But sorry, I mean our just our sets as which generate localization, and if we denote this construction by S from CD, where C is cofibrant objects and D is natural number, it is easy to see what sigma functor is just on these maps is just this, and definitely all such maps is weak equivalence here, because we know what, no, by definition, in stable model structures, omega spectra is exactly fibrant objects. So no, you can easily to check what if you have any cofibrant objects, these maps will be weak equivalence, because it induced weak equivalence on map in any omega spectrum. I already write it here, sorry. Okay, so we have this Quillen adjunction for a stable model structure, and now we want to show what this is really Quillen equivalence. This means what on homotopic category in usual one localization is Quillen equivalence. Of course, in real, if you have any no, I just want to say that if you have any Quillen adjunction which is equivalence of on homotopic category, in real this means more. This means what? No, it's really right equivalence condition equivalence definition for model category. For example, always. No, I mean it can be seems like. Some strange or small condition, you only demand with on no один localization on homotopic category, but we often want to say about derived map, which not just set of maps, but no simplicial set homotopy types of maps. And no, I mean you can wonder in questions. It is true if this for middle category you have Quillen equivalence. It is true something like this, because by definition we demand this only on P0 from derived map, only on maps in homotopic category. But in real, of course, we want something like this. But no, but this is true. It is turn. No, what we if you no, you can prove it in just in formalism in male category, for example, and no, with some technical assumptions. And for example, in if you will use infinity category setting, you have functor from middle category to infinity category, which gives us infinity localization, and every Quillen adjunction gives us just adjunction in infinity category sense. So it's right conception. Consider for proof this fact, consider another Quillen adjunction. Just shift. No, how I write it here? Shift in left and in right, and obviously with adjunction, and obviously this functor preserve. One second. Obviously, this functor preserve fibrations and weak equivalence in level-wise model structure. So this is Quillen adjunction in level-wise model structure, and now since this functor preserve our set of maps for localization, is in real this functor is left Quillen functor from already stable model category, and we get it. And the theorem. Both this adjunction, this Quillian adjunction for stable model category are Quillian equivalences, and Hovey here, Hovey said here what this functor always same on one localization on homotopy category of this model category, but again, this is true in more sense with the same functor in infinity sense in particular. Yes, so let us prove it. Consider with canonical maps. I should maybe remind what this map is just from definition omega spectra. For us, when we have sequential spectra, we take omega object-wise, and then we do shift to left, sorry, to right. Yes. Strange, sorry, 1 second. Maybe this is typing. No. 1 second. Yeah, I just typing here. Now takes left. When is because what, for example, take some sequential spectra when take T functor, and we have point here and maps to this should be the same what Yes. A T from A, B S from B. T is left functor, B is right functor. Sorry. Yeah, so this from just from this map from definition omega spectra. By definition omega spectra, this should be weak equivalence.
Okay, and the top equivalence, the one which involves sigma and omega, are they Quillen equivalences with respect to the Quillen model structure, I presume? With respect to the stable model structure, is this correct? Верхняя эквивалентность, значит, сигма и мета. Она в какой модельной структуре? В стабильной или в...
Understand. Now we only know what we have two adjunction, TS and sigma omega, adjunction on both model structures, and levelized and stable with correct define.
Okay. Do we already know that the stable model structure?
We don't prove any about equivalence. No, we want to prove that both these functors are Quillen equivalents, and in real it's the same Quillen equivalence in this sense, but we don't prove any factor. We just consider these maps for fibrant object. So what I write here, what with the equivalence, if and only if by definition X is fibrant, because it's exactly omega spectra. When by this reason, because what this is right total right derived functor from Quillen functor, how I define it when recall on how Quillen adjunction give us adjunction on homotopic category. So when we apply right derived functor to this natural transformation, we get isomorphism between identity functors and these functors. And I should maybe recall what total right functors calculate next as follows. First, you can fibration replacement when you just take your functor, and so if X or if brain, you just take your functor, and we see this.
Я все равно не понял. Мы уже построили стабильную модельную структуру, или мы пока еще не построили ее?
We construct stable model structures here.
А мы доказали, что слабая эквивалентность это выражение, которое индуцирует ля-ля-ля.
This is our goal for today.
Хорошо. So we have a model structure on spectra, which is in fact the stable model structure, but we haven't shown it yet.
Yeah, we can say it in this way, but also you can think what this general definition stable model structure in general context, because you can do all this in any model. What if you have initially model structure with some soft good assumptions and some left Quillen functor, any left Quillen functor, you can do all this and then have some stable model structures in this sense. And now we prove what in usual case, like topological space, it's the same what Quillen equivalence detects on stable homotopy groups. No, this is wife point of Markovy, my general source for this talk. Markovy works. Yeah, so we prove it, and then since it's easy to see what these functors commute, we get isomorphisms with identity functors. No, I mean, we have natural isomorphisms and these natural isomorphisms. So we prove what this is Quillen equivalence. Yes. And now already when we prove what every from this when we prove what these functors and these functors on homotopy category give us equivalence, so this should be this and this should be 2 because on homotopy category these functors are joint and this equivalence, so this also equivalence. Yeah, this we proved the theorem. Yeah, and now we need for next considerations, we need assume what our category of space finitary generated. We already have cofibrantly generated and we work with combinatorial model category, cofibrantly generated and locally presentable. But now we also want to assume what is finitary presentable. So our cardinal in definition is natural numbers. So we have dense generator of just compact objects, and we assume what domain and codomain generated configurations and trivial generated configurations is compact finitely presentable objects, synonyms. And in particular, this means what fibrations closed under filtered limits. Because fibrations define this is acyclic fibrations, and the fibrations define right lifting property respect to them, but with compact objects. So if you take filtered limits, fibrations maps to high limit always factorizations across throughout some objects in diagram, and obviously co-limited fibrations, and also omega functor in top and pointed top with such property will be finitary functor, also preserve filtered limits because if S1 finitary and with do because it's domain some generated configurations is finitary, you have what you want to prove what internal home preserve filtered limits, but no, check it on take some K from dense generator of compact objects, because our category finite representable takes some generators. For example, in delta generated space, we want to take some simplex, and also in simplicial set we can some simplex, but delta generated is not finite representable because simplex are not compact. We need more cardinal something like no, never mind. And more cardinal, not natural numbers. But however, we take some objects from our dense generator and test with home. This give us such map, and we need to know what these objects also compact. Product compact objects in general not compact, but but it should be here because should be here true because I think because category extensive, something like this. No, I mean we know it in general in concrete examples. Not now I give as concrete examples. It will be obvious in this, and in general maybe I should think about conditions for this. And so maps to Calimit factorizations, and we have what we want. Okay, some examples for this such model category for homotopy theory. Primary examples, simplicial set. It's just any preshift category is locally is finitary representable. Any preshift category is preshift on simplex category. Simplexes will be generators, and home from simplex just preserve all colimits at all, not only filtered colimits, because colimits in category functors calculate in object wise. So objects from category in any preshift category always preserve all colimits. With covered teeny objects, and yeah, is our dense generator here. But sometimes no, it's very good. It's simple model for homotopy theory, but sometimes we want some geometrical, I mean, topological arguments. For example, in K theory, when we want talk about bundles, and sometimes it's really helpful for homotopy theory, not only discrete similar simplicial complex. And in this case, we can use model which we right now discuss, but no, but here I mean not smooth maps, but continuum maps. No, I mean, so I just take card as full subcategory topological space. What if we close this under colimit in top, we get exactly delta topological space. But this good, but not good enough for us now. Not finitary representable. So we can just consider sheaves on this category, how I explain right now, and this already finitary contain delta top as full subcategory with exactly concrete objects here, I think. And what so you can take or this, it is will be work. Sorry for my very bad English. Okay, define now finally notation for this construction, which we already many times used, and no, but by sense and stable sense, we just don't do nothing with the same objects. But for on model level, it is exactly what we need for construct configuration replacement, which the same object in stable sense, but not in other sense, but not the same on strict level model category. And yeah, we define infinity powers or with omega shifted functors, and it's easy to see what these maps is, of course, just just E from these objects. I think we all remember what we have E, what we discuss it here. What? Oops. I. And by this, it's easy to see what when we take infinity limit, this will be already no, how it called in English? No, I mean constant point by action with functor. This already will be isomorphism. So so we can note what if we start with a fibrant object in our category in very sense, when our replacement is really omega spectrum. Just by this reason, because for omega spectra we need what this map will be weak equivalence, but this is just isomorphism. When noted what if X was omega spectrum, when these maps from X to this replacement is well-wise equivalence. Actually, what consider by definition we know what this map weak equivalence from Ix from X to shifted omega. When we can take any factorization in configuration and configuration, and when we take factorization, one from these maps in general will be weak equivalence. We have factorization in weak configuration and fibration or with zero. But since composition already weak equivalence, both map will be weak equivalence by 2 from 3 rules. So both maps weak equivalence, and when we repeat this construction, so we construct what no new object y1, and maps from y1 to these objects also weak equivalence, no, because with weak equivalence, with weak equivalence, and we just apply right equivalent factor to weak equivalence between fibrant objects. So with weak equivalence, and again we have this factorization and repeat it when take a limit. In this line, we have limit trivial configurations, and trivial configurations already closed under transfinite composition as any left class in if you have just any par class maps, and more general, if you have any maps of set of maps and you take left class of S, or maps which left via orthogonal all maps from S, this always closed under transfinite composition. But here not trivial in general. Sorry, not here. I mean what filtered colimit is weak. Is trivial fibrations will be trivial fibrations. But we assume it. We assume what our category affinities, so fibrations closed by this reason. Fibrations closed under filtered colimits. This is true in simplicial sets and shifts on the Cartesian space. So we have factorizations our map from X to omega infinity from X in composition to V equivalence. So this is V equivalence. We prove it. Oops. When it means what map is stable equivalence. If and only if we check what this equivalence for strict omega spectrum. By definition, we know what this is true when we consider here any omega spectrum. Omega spectrum is well-wise Sibrand, and this map is weak equivalence. But by this prop, we can consider only a strict omega spectrum when this truly isomorphism in sequential spectra. Because every omega spectra is weak equivalent strict spectra by this proposition. So now show what if this replacement from some maps is well-wise equivalence, when this maps stable equivalence is critical proposition. What we want to show what morphisms, what stable equivalence detect by this replacement. No, we already know what this is. It was obvious by definition what this is fibrant replacement in stable model structure, but because it's just strict omega spectrum by this proposition, and of course omega spectrum, and now we prove what with the text stable equivalence. Okay, how we will do it? Consider any strict omega spectrum and derived home from our morphism to this omega spectrum. No, derived home in sense sequential spectrum with well-wise model structure. I mean, so if we show what is retract with derived home, we win. We win because with derived home, weak equivalence, we consider derived home from morphisms to objects. So this means morphism between two homotopy types. Between two space with morphisms, and this derived form is weak equivalence by definition because we assume that this morphisms is weak equivalence. So if we retract weak equivalence is also weak equivalence, and this is enough because we want what enough check weak equivalence on strict omega spectrum. No, and this is obviously actually because we just can construct both maps in this direction. We use it. If we have any maps from between replacement, we just consider composition, and here we use what this strict omega spectrum. So we have in any object we have this map by definition map to co-limits, but since X is strict omega spectrum, we have map this is isomorphism, and we have morphism in opposite direction. And here we just apply this functor just apply to this functor to morphism between these objects and get morphisms here. But here's very some technical moment because always model category is about controlled some homotopy infinity concepts with strict level, and but we need by this reason we need think about Fibonacci replacement, covariant replacement, and often work with some technical conditions. This is exactly sense of model category. And here we have some technical conditions when some functor from model category to model category, right-wing functor, when we can just apply it just apply it to morphisms in model category, and this really get us morphism from derived home to derived home. Here for this enough what in any model category enough what with just preserve finite products and weak fibrations and weak equivalence between fibrane objects. Two conditions: fibrations between fibration objects and weak equivalence between fibrations objects. So it's obvious for this functor because it's nuclear right functor, and sorry, what I say? Why? Really obvious was this? Maybe not, but maybe this is not obvious. 1 second. No, anyway, these conditions obvious because fibrations caused under filtered co-limits from definition of this functor, and so on. in particular, this means what this map is stable equivalence. So it's really fibrant replacement, not just some functor which give us some fibrant objects, because if we apply to this map this functor, it will be isomorphism. Finally, if we just say what we already prove in one theorem, we prove what map from any sequential spectra to this infinity power from shifted omega spectrum from A is stable equivalence, and this is omega spectrum. So it's in other words, it's fibrant replacement in stable model category. So our stable model structure, I mean, and also map from map between spectra stable equivalence if we not leave is well-wise equivalence on fibrant replacement, our canonical fibrant replacement, and say second in other words, maps is stable equivalence if not leave is isomorphism on all stable homotopy groups, because stable homotopy groups from maps is homotopy groups from some component in sequential spectra, in the condition what if we know what these maps is weak equivalence for all n, so this isomorphism, and we get this implication opposite if we know what all these isomorphisms, we have what all this map is weak equivalence. So by this theorem, we have what this is stable equivalence.
Okay, well, this is what we wanted to prove.
Yes.
Very well. Are there any questions? Well, looks like there aren't any questions. So, Ashok, thanks for your presentation. Please send me your notes so I can post them on the web page.
Okay.
Okay. Well, let's have a break until 6 o'clock. I'll stop the recording.